Over the next two sections, we look at some safety and design considerations because of the fact that our battery packs are very high voltage. Um, in particular, the battery packs are designed to be completely isolated from chassis ground. So in a vehicle application, we would have the chassis, um, which is just the steel frame of the car. And then there's usually a 12 volt battery, and the plus line gets distributed to different circuitry, but the return or ground is actually the chassis ground. But for a high voltage battery pack, both the plus and the minus lines are distributed everywhere they're needed in the car. We never actually use the chassis ground. And the reason is the chassis ground is very easy to grab onto in different places if you're a mechanic, or even if you're just like closing the door or something, you're touching the frame, and if the paint has come off, you're touching the metal directly. So you're already touching one branch of the electrical circuit. If you happen mistakenly to touch the other branch and it's 12 volts, almost certainly you will cause no damage to yourself, but if it's a very high voltage, you almost certainly will cause significant damage to yourself. So in the following section, we're going to look at how to measure the isolation of your high voltage battery pack to ensure that you are actually isolated. In this section, we're going to focus more on another issue related to the high voltage, high current nature of a battery system, and that's how do you connect the battery to the load. It sounds like a simple thing, but it takes some consideration to do it properly. So when the battery system is not in use, the high voltage bus is completely disconnected from the load at both terminals. Again, we want to minimize the possibility of someone mistakenly touching both terminals somehow or other and electrocuting themselves. And one way of minimizing that possibility is to simply disconnect the battery pack from the external terminals of the battery pack when it's not in use. So in order to disconnect, I've got the high voltage line of the battery pack. I need basically a switch between it and the outside of the battery pack, the load. I need two switches, one on the positive terminal and one on the negative terminal. And these switches are electronically controlled, and you could call them relays because of that, but they're usually called contactors. Slight differences perhaps in the manufacturer, but they're high voltage, high current switches inside of some kind of a container that's usually evacuated. There's usually vacuum or some inert gas in there to minimize the possibility of arcing across the terminals of the relay due to ionization of the gases inside. So I need two switches, and that's fine. But the load usually has some capacitive nature to it, especially if I have a motor control, because the motor control itself has a lot of switches, which adds a lot of noise, and they put capacitor banks on these switches in order to kind of smooth out the load demand. So a capacitive load is not uncommon. And if I were to close both of these contactors at the same time, they would the current would try to charge up this capacitor instantly, because there's essentially no resistance or extremely little resistance of the wiring between the battery pack and the capacitor, and an enormous amount of current would flow out of the battery pack, which is going to exceed the design limits of the wiring, and furthermore, it could cause arcing inside of the contactor, even across a vacuum, and that could cause welding of the terminals so that they could never open again, so you'd always have just a contacted contactor. Or you could even blow a fuse if you have a fuse in your battery pack, and you probably do. So the simple thing of just closing a switch doesn't work. We need a different approach, or a refined approach. What we end up doing is using a third relay, or a third contactor, called a pre-charge contactor. And the focus of this section of notes is to go through the steps of how do you connect the battery pack to the load using this pre-charge contactor. So I have a lot of pictures showing stepwise the process. They're all very similar to each other, so let's look at this first picture here and look at the details of the picture. First, on the very left, we have the high voltage battery pack itself, and I've drawn some number of cells, but there could be quite a few there. There could be hundreds. There's a fuse in the middle of the battery pack, and that's pretty common because if for some reason the battery fails and we want to open up the case and poke around inside, if the fuse is in the middle, that breaks the voltage of the battery pack in half. Again, we're trying to minimize the possibility of electrocuting the technician or whoever's looking inside the battery pack in this case. And so putting the fuse in the middle is one way of at least helping with that. The red boxes are the contactors. There's 3 of them. There's one on the negative terminal of the battery pack, so that's minus down here, and there's one on the positive terminal, that's plus, and then there's a pre-charge contactor as well. So looking at the negative contactor, the symbol here, this bar, indicates whether the contactor is open or closed, and you see the bar is floating above the contacts underneath it, so it's drawn in this case as being open. There's no connection. And then there's a coil, because the coil is what activates the contactor. And all 3 contactors are presently in an open condition. This is how you would store the battery pack. And we can see by the thick lines coming out of the battery that the high voltage gets only as far as there, or there, or there. The thin lines on the other side show that the voltage is not connected, and so the bus voltage we would measure 0, whereas the pack voltage we would measure the high voltage, whatever it is, 300 volts maybe. The first step we take when we are powering on the battery pack or connecting the battery pack to the load is to activate the negative contactor. And you can see that this line is now drawn as thick, showing that we have connected that line. And this line here is shown as thick, saying that we have also connected that line. So since this entire coil is activated, it's drawn as blue instead of black. And we've drawn the connection here, showing that, oh, this contactor is closed. The other contactors are still open. Yes, they have power applied to this terminal, but they do not have power applied to the other terminal, so the coil is not actually activated. It's only the negative contactor that's activated, which means that the bus negative terminal is now directly connected to the battery negative terminal, but the battery positive terminal does not go all the way out to the bus. So this is still a safe situation. It's the first step of our powering up. So we proceed. The next thing we do is we activate the pre-charge contactor. So we keep the negative contactor activated. It's activated the entire time the battery pack is in operation. But we want to apply power to the positive terminal here of the load, and we want to do it in such a way that we limit the current that is flowing to the load to charge up the capacitance of the load. And that's where the pre-charge resistor comes in, because when we power up the pre-charge contactor here, now this side is powered, that side is powered, the whole coil is powered, so that closes this switch. And looking at what is connected to the load, I have that path is connected to the load. So we have intentionally inserted a resistance between the battery pack and the load to limit the amount of current that can flow. And the idea is the RC circuit of this resistor and the capacitance of the load will slowly charge over a matter of maybe a second or so in a very controlled way. And then this voltage here will come to the neighborhood very close to the pack voltage, and then and only then is it safe to close the positive contactor, the main contactor. So that's what we've done now. So all of the contactors are presently closed. And I have a direct connection to the battery there. And I still have this resistive connection, but in parallel I now have that connection. So because this connection has essentially zero resistance, whereas this connection has a lot of resistance, this connection is preferentially used. It's just using circuit analysis techniques, we know that. So I now have full voltage across the load. Now, this voltage over here was maybe not quite equal. The bus voltage might have been not quite equal to the pack voltage. So why was it safe to close the positive contactor? Well, because it was pretty close. The capacitive load still needs to be charged a little bit, but not so much. And so I will not have any, when I close this positive contactor finally, I don't have an enormous outrush of current. The capacitor will charge and everything will be fine. At this point, it's safe to deactivate the precharge. So that's the very last thing that we do. Is you'll notice that this line here is deactivated. I don't need the precharge circuit any longer. And now the pathway is through the battery pack, just like this. And I am completely connected to the load, and operation will continue just as normal. Because the precharge resistor is limiting the current flow through this branch, the precharge contactor does not need to be as big, to have as big a sizing as the positive and negative contactors do. And we do have to watch a few things, though. For example, there's the possibility that the load out here is somehow faulted. So I'm going to need to make sure the precharge resistor does not get too hot, because I'm continually drawing a lot of current through it. If it gets too hot, I just have to open the precharge contactor and declare some kind of an operational fault. If it takes too long to charge the capacitive bank of the load, that probably means there's a load fault also, and we probably want to open the contactor and declare that we think that there's a problem. But normally what you would do is you would monitor the bus voltage and the pack voltage during the precharge, and when they get close enough, you will then close the positive contactor. To do that, you're going to need a pack voltage sensor and a bus voltage sensor. And we already measure all of the cell voltages, so you might add them up simply to get a pack voltage. Or alternately, you could have a high voltage A to D also that measures the pack voltage as a kind of a backup sensor. The bus voltage you can get away without if you recognize that if I put a current sensor in here, measure I, actually current usually goes the other way, measure I, then if the pack voltage and bus voltage are the same during a rest situation, then I will go to 0. So we can use the current sensor and the voltage sensors to infer if the bus voltage is close enough to the pack voltage. So that's another possibility, so we don't have to actually measure the bus voltage directly, and we can use the sensors we've already talked about. So that is the startup procedure of a high voltage battery pack. It's once you see how to do it, it's not very difficult at all. You just have to make the circuit to do it. The procedure for shutting down a battery pack is probably not quite as clear what to do. If we are in the middle of a dynamic operation, the battery pack is powering the load, and for some safety reason I decide to disconnect the battery pack from the load. First, we would almost never do that. It would be under a very extreme condition we would disconnect while we are actually powering a significant load. But if I do that, that might cause arcing and welding as the current tries to flow through the vacuum of the contactor. The capacitive nature of the load might store enough energy, though, to prevent this, so that there will not be arcing when I disconnect the contactor abruptly, and the capacitor will power the load for a few milliseconds, and then the load will just kind of coast to a stop, I guess. It's possible you would want to activate a pre-charge path parallel to the main path before you disconnect the main path. I'm not really sure I know the advantage of doing that, though, because again, the capacitor of the load is already charged to the right level because I'm connected to it. So there's not an obvious benefit of connecting the contactor again before disconnecting everything. And that could possibly blow the pre-charge resistor if I'm trying to draw a huge amount of current through it when I disconnect the main path. But the capacitive load might save the resistor also. So the pack shutdown is a little bit less clear what to do. You might try both of them in your application, but the pack startup is the pre-charge resistor is definitely a requirement. Otherwise, your contactor is not going to live a very long life. So that's the power on process, and it has to do with the fact that very high voltage battery pack powering a very big load, a load that draws a lot of current. The next topic we're going to look at also relates to the high voltage nature of the battery pack and safety. And so we're going to look at the how do we know that the pack is actually isolated from the chassis ground, and what kind of process can we undergo to ensure that that's the case.